Hi guys, this will be a quick recording on the different sections under memory management, specifically paging, segmentation, page faults, and page replacement algorithms. Let's get started. We'll start off by looking at the different aspects of memory management. Now, memory management can be either contiguous memory management or partitioned memory management. Contiguous memory management is when the entire RAM or the entire memory is allocated for a single application. Partition memory allocation is when a single memory or the entire memory is allocated for multiple applications, and we refer to this as multi-programming. And it is with partition memory that you can go in two directions. You can either partition the memory to be dynamic partitioning, which is referred to as segmentation, or you can partition it statically, which is referred to as paging. You need not know the different terms here, static, dynamic partitioning, but you should know that partitioning falls into two different categories called segmentation and paging. So in overall sense, contiguous is when you allocate the entire RAM for one application. Partition is when you allocate the entire RAM to multiple applications that can be of one of two forms, beg your pardon, segmentation and paging. Let's start off by looking at how segmentation works. Remember, for this section, to really understand this section, you should understand the difference between logical and physical addressers. Logical addressers are those created by applications and respectively the CPU that essentially help the CPU keep track of what memory the application is requesting. But the physical address is sort of the exact location where that logical address is pointing to in RAM. So remember, a logical address is sort of like a fake address that the CPU or the application would be using for internal reference, but physical addresses are like the actual addresses that those logical addresses map to that is actually in the RAM. Now, in segmentation, let's say that you're trying to access an application in RAM. Those applications will be divided into segments. That's where the term segmentation comes from. Segments are variable size blocks of memory that belong to each application that is running in your computer. And remember, these variable size segments are of variable size. What does that mean? That they can be of different sizes. No two segments have to be the same size. Now, let's say that you're not, let's say you have 5 applications running right now, and these 5 applications have 5 segments. Let's say an application or the CPU is trying to access the fourth segment. That 4 is your segment number. And let's say you're trying to access the third memory address within that fourth segment. The third memory address within that fourth segment, because a segment is made up of multiple memory addresses together, right? That's referred to as your offset. The segment number and the offset together forms what you refer to as your logical address, a reference to the actual address in RAM. It's a reference, not the actual address itself. What's going to happen is the CPU is going to ask the memory management unit, which is a component inside the CPU, to look this segment number up on a segment map table, which is essentially a data structure that is stored also in the RAM that contains the segment numbers, the logical addresses per se, and their respective physical addresses. Where are these segments in physical memory? And also their sizes. We'll see how the sizes are important later. Now, what's going to happen is the memory management unit on behalf of the CPU will be looking up the segment number 4 in the segment map table, searching one by one to get to 4, and then locate that its memory address, physical memory address is 600. Once it finds 600, the MEMU will sort of retrieve that 600. But before it does anything with that physical address, it tries to check whether the offset, the memory address I'm trying to access within this segment, is less than its size. Essentially, let's say my offset is 21. I can't access an offset of memory addresses 21 in a segment that is only 20 blocks long, or 20 memory addresses long, right? That can't happen. So the memory address does a small limit check rather, which checks whether the offset is within the limit of the size. Here 3 is less than 20, so this action is permitted. If this fails, this is what results in what we refer to as a segmentation fault. You're trying to access data that is out of your segment, and this is an example of how memory protection is established by the operating system. Now, moving on, what happens after this is once this validation takes place, the address that you retrieved of segment 4, the address 600, that is actually where the segment 4 exists in RAM, that is going to be retrieved and added to the offset. To locate that, this actual memory block 4, this segment 4 is located at which address? 603. The segment itself is at address 600, but the specific address, the specific offset you are looking for added to this address would result in a final physical address of 603. And what's going to happen is the CPU is going to direct this physical address to be read from the RAM via the address bus. So really what happens here is 603 is going to be looked up in the RAM, and the respective process is going to be retrieved to the CPU. And remember, this entire block here from 600 to 620 belongs to segment 4. And why is it 600 to 620? Because based on the segment map table, segment number 4 has a size of 20. Okay, that's done. That's how the segmentation process works. In summary, segmentation involves variable size segments. The user can control the segment size. That is, the user can manipulate, or the application on behalf of the user can manipulate the size of the segment. And to translate logical addressers into physical addressers, it uses a segment map as well as a memory management unit. You learn what the memory management unit does. What does external fragmentation mean? It essentially means that between segments there might be free space that might or might not be allocatable, because some segments might be larger than the size in between these sort of segments, and this results in wasted space in between segments just because these segments have variable size. So when there is fragmentation of segments externally, meaning there is empty space between segments, we refer to that as external fragmentation, that results in the wastage of RAM's memory location. It just wastes RAM. There is enough space, but that space cannot be used because it's broken up. Right. That's about it for how the respective operations for segmentation works. Now we will take a look at paging. Paging divides your RAM into fixed size blocks, which are usually all 4 KIB in size. 4 KIB in size. And essentially what happens is these fixed size blocks in physical memory RAM is referred to as frames. But in logical memory, the CPU's own version of this RAM that it's going to use for its respective applications, the virtual copy of it rather, it's a fake copy, right? It's not the actual RAM. It's sort of like a local copy of it or a local reference to it that each application maintains. These frames in that form or in the logical address space is referred to as pages. So what you need to understand is, in terms of logical memory, these fixed size blocks are referred to as pages. In terms of physical memory, these fixed size blocks are referred to as frames. What happens is the CPU would propose a page number that it wants to read. Let's say, just like the segment number earlier, we are trying to read a page number of 2. We are trying to access this application number 2 in the RAM. We have a page table just like the segment map table that maps each page number to the frame number. What's going to happen is we're going to search for page 2 and realize that its actual frame number is 7. This basically says that if you want to find out page 2, you need to go to memory address of frame number 7 in the physical memory. Then what's going to happen is the memory management unit is the one that's going to look this up, and it's going to find this number 7 in the RAM, and here at address 7 or at this frame number 7 in the RAM, this application B2 is what's currently stored. So that process is retrieved to the CPU. Remember, for those of you that might be looking this up online, there's usually another component called the offset, just like segmentation, that is attached to page numbers. But again, that is out of the scope of this section, so don't worry about it. Again, page number is requested by the CPU. The page number is looked up in the page table. The respective frame number is looked up by the MMU, and the respective frame from that frame number is retrieved for the CPU. And remember, one application may have multiple pages because it might not be feasible to fit everything into one page, right? Like I said, one page only has 4 KIB worth of space. So therefore, one application, this application B, has a total of 4 frames. Likewise, this application C has a total of 3 frames. Depending on the application, it might have multiple frames, right? So we learned that pages are fixed size. So therefore, paging memory systems would use fixed size pages. The hardware is what decides the page size, because the amount of RAM dictates what the size of each page should be. It's not like the application can determine the page size. The page size is fixed regardless of the application. You can allocate more than one frame, but that doesn't rule out the fact that each page must be the same size, and thereby, by extension, the frame must also be the same size. And for translating logical addresses to physical addresses, it uses a page table and the memory management unit. Earlier, we learned about external fragmentation. That is essentially when there is space left out between segments. What is internal fragmentation? This is a sort of problem that paging suffers from. For example, let's imagine that this application B had 5 frames, that it had to be loaded into the RAM, for example, at 5 frames, and you only had space for 4 frames. And let's imagine hypothetically, right, this C3 was empty. I mean, this location number 12 was empty. So you need 5 frames for B, the process B. You can fit 4 here and you can fit the 5th one here, B5. But what that's going to do is it's going to sort of separate out these applications data to be non-contiguous, right? Application B's frames are now split up because it didn't have contiguous memory space for it to be located. So therefore, we refer to this as internal fragmentation. When there is not enough contiguous space in the RAM, and this usually happens as a result of paging in and out, which we'll look at under virtual memory. This results in internal fragmentation, essentially when an application would have to split up its frames because it does not have a full stretch of contiguous frame locations. But yeah, these are the features of paged memory and its respective, actions. Now that we looked at paged memory systems and segmented memory systems, and you understand the features you need to understand for the exam, we can now look at page faults. Now, let's imagine, unlike earlier where the CPU was requesting page number 2, the CPU is now requesting page number 4. What's going to happen is page number 4 is going to be searched up in the page table, and it's going to try to retrieve the frame number but realizes that the frame number is invalid. This means that the page exists in the logical memory, the page number exists, the application needs this page, but it has not been mapped to the physical memory. It's there, but it's not there in the physical RAM. That means that it must be somewhere else. What that means is that somewhere else is referring to the hard disk drive. For example, when applications come in and go out to the CPU or go out to the RAM, there might be spaces that might be freed and occupied, for example, and these set of operations, freeing, occupying, swapping in, swapping out, can result in some frames of in this case some frames being swapped into the hard disk drive. And what this means is when this happens, the page table might not have been updated as a result of it, or due to some issue the frame number would have not been recorded. And what happens is when the page is trying to be looked up, the frame isn't available. In summary, what's happening here is a page exists in logical memory, but this respective frame doesn't exist in the physical memory. That's what happens. So this is the case with page number 4. This is what results in a page fault. A page fault is a hardware-based interrupt caused by a running program requesting a page that has not yet been loaded into the physical RAM, which means that this page is either not yet loaded or is in virtual memory. And virtual memory here refers to these sort of pages or these frames rather being loaded into the hard disk drive, which we'll look at later. But again, when this happens, it's going to result in an interrupt, which we refer to as a page trap that is sent to the CPU. It's a hardware interrupt called a page trap, that's essentially going to tell the CPU to stop whatever the hell it's doing and service this interrupt. And how does it service the interrupt? It's basically going to try and search for this page number 4, in the hard disk drive space. There is a space in the hard disk drive called a swap space where some of these mislocated pages might be stored. And it's going to basically search through this swap space, and let's say luckily we find it. When we find it, it's going to return that page 4, the frame respective to this page number 4, and it's going to be loaded into the free location in the RAM. Now, wherever there is space in the RAM, it's going to be loaded, and the page table is going to be respectively updated. Now, here it says 4, but essentially, if the frame is found in the hard disk drive and it's not there in the RAM, this frame number would be updated to take account into where this page is now stored. So for example, it might change into something like 23, and 23 might be referring to the frame number which is in the hard disk drive. Okay, so that seems like a lot of stuff to grasp, but in summary, what's happening here is page faults occur when a page is trying to be requested from the page table by the CPU, but it doesn't exist yet in the physical RAM, or it has been loaded into the virtual memory. So this results in a page fault. What do? The CPU is sent a page trap, a hardware interrupt that tells the CPU to service this interrupt, fix this problem where the page is not getting translated to a frame. And therefore, what the CPU does is tries to search for that frame in the hard disk drive, loads it into the RAM, and updates the respective page table to take into account where that frame is now stored. So then from that point on, the CPU can rerun this process and finally load the frame properly into the RAM. Essentially what I mean by loading is to run that application properly without encountering a page fault again. All right, just see if that makes sense. And if if it doesn't make sense, please get back to me. Now, looking at virtual memory, how does virtual memory work? Essentially, let's say that we are using a paged memory system where we have these frames in the RAM right now, and the CPU is trying to load a new process D, into the RAM. And let's say that process D has 5 frames to be loaded, D1 to 3 through D5. What's gonna happen is it's gonna search for any free locations. It turns out that 10 to 12 was free, and it might load the first 3 frames, D1, D2, D3, into the RAM. That works properly, but then D4 and D5 are remaining. D4 and D5 seems like they don't have space. So what does the CPU do? The CPU removes 2 frames from the hard disk drive. How it makes this choice, we will learn about under page replacement, right? CPU removes 2 frames. Essentially, what happens is the least frequently used pages are going to be swapped out of the RAM into the hard disk drive because they are less important. The user wants to run this process D now, so that's more important. So whatever least frequently running processes, let's imagine that's A2 and B1, are going to be loaded into the hard disk drive, swapped out into the hard disk drive from the RAM, and D4 and D5 are going to be put into the RAM, to make space for it. And essentially, as a result of doing this, so that we don't encounter a page fault again, what we do? The frame numbers must be updated on the page table to take account for the new places that the A2 and B2 frames were transferred to. So again, remember, in virtual memory, you essentially extend your RAM using the hard disk drive to temporarily swap pages in and out depending on necessary. So here, D4 and D5 didn't have space. They were given space by swapping out A2 and B1 into the hard disk drive. And this gives the illusion of having unlimited RAM to every single process. This is how virtual memory works, guys. Once again, in summary, what happens is you would basically have a process that requires space, but that process doesn't have space. So the respective processors frames are swapped. Oh, I have to make a clarification there. When a process tries to come in and it doesn't have space for it in the RAM, what's going to happen? The respective frames of some other process that are least frequently used will be swapped out of the RAM into the hard disk drive to make space for these new processes that need to come into the RAM. And again, it might not always be done in terms of least frequently used priority. The way that these pages are going to be replaced by someone else is going to be dependent on the page replacement algorithm, which we'll look at next. So this is virtual memory, and essentially it's a way of extending the RAM using the hard disk drive to give apps the illusion of having unlimited RAM. Now, once that's out of the way, we will take a look at page replacement algorithms. Now, like I said earlier, page replacement algorithms take place when a process requesting RAM results in a page being swapped out into the disk to make space for this new process. So essentially, that's a process that's coming into the RAM. That process doesn't have space. So what page replacement algorithms try to do is figure out which process that is currently in the RAM do we swap out into the hard disk drive to make space for the new process. That's what page replacement is, and page replacement algorithms try to figure out which process do we choose to swap out to make space for this new process. It's essentially used in accompaniment with virtual memory. The first method of page replacement algorithms is first in, first out, where what you do is you maintain a queue of all the pages currently in the RAM, or essentially a queue of all the frames per se. Again, the terminology doesn't have to be that specific here, but it's best if you refer to it if you refer to it as pages. You keep a queue of all the pages that is in the RAM right now, and when you want to, let's say, bring in a new page or a new frame into the RAM and kick out one of the existing frames or pages, what do? You choose the one at the front of the queue to kick out. So the page is dequeued, and that page that was dequeued is the one that is replaced by a new one. So essentially, if you think about how a queue works, whoever is at the front of the queue would be the one that stayed in the queue for the longest time. So therefore, who's going to get kicked out is the oldest page, or the one that first arrived in the queue. So remember, first in, first out page replacement basically kicks out the one that has stayed in the RAM for the longest time. This might or might not be the best choice because people, or frames that are in the RAM for the longest time might still be under some kind of processing. But this is just one way that you can solve this problem. But the thing with this problem, or not the thing with this problem, but the thing with this algorithm, the thing with this first in first out page replacement algorithm is that it suffers from something called Bellardi's anomaly. Bellardi's anomaly is essentially when you have an increasing number of faults as the number of frames increase. Now, how first in first out works is you maintain a queue, you swap the new process with whoever is at the front of the queue by dequeuing who is at the front of the queue. So think about having a lot of frames in that queue right now. Let's say that you have a lot of frames in your queue. Let's say you have a lot of pages in your queue. The more pages you have, the more likely that you're swapping out something that is actually necessary, right? Because of the way that this algorithm works. You might be swapping out a page that is actually currently required for processing, and therefore what's going to happen? The more pages you have, the more frequency of page faults. What do we mean by page faults? The more frequency that you're actually going to need a frame that you just remove, if that makes sense. So as a result, what's going to happen is the number of page faults is going to exponentially increase the number of frames, and this is what Bellardi's anomaly is. It's essentially when it's the problem that FIFO suffers from, where the more frames you have, the more likely that you're replacing a useful frame with something that is currently running. So it's not the best algorithm to undergo. Technically, your best case scenario should be an algorithm that reduces number of page faults as the number of frames increases, and that is what our next algorithm does, called OPR, optimal page replacement. Optimal page replacement is a theoretical algorithm. It cannot be implemented literally, right? It's a fake, if not a theoretical algorithm. It looks good on paper, but not practically. It can't happen practically. The way that optimal page replacement works is it determines which page will be least used in the future and replaces it. Unless you have a time machine, this doesn't work. But that's just a theoretical thing. Essentially, what you do is you look into the future, see in the future which page might be used least, and you swap that out into the hard disk drive, and therefore you make space for the new process. This is basically the best case scenario where you're basically swapping exactly what is not required and swapping in what is required. And therefore, if you think about it, you're gonna basically swap out exactly what you don't need and keep whatever is required. Therefore, this is a theoretical best case scenario algorithm that is just used as comparison or status quo for the other algorithms, right? Then we have least recently used, which is what I talked about earlier. The pages that have not been used for the longest duration is replaced. Essentially, when a new page comes along, we choose which page has existed in the RAM for the longest duration but has not been used, and we swap that out with someone new. And this is what's most practical and most efficient to do. But again, page replacement algorithms aren't that difficult. They are just algorithms that are used to that are used to determine which process or which page or frame do we swap out of RAM to make space for a new frame, and therefore it is used in accompaniment with what? Virtual memory, to try and limit the number of page faults. Remember, page replacement algorithms' end goal is to reduce the number of page faults. It's synonymous to how process scheduling algorithms, their goal is to reduce the number of processors waiting or to minimize the waiting time. So here, page replacement algorithms, their job is to essentially reduce the number of page faults. So we discussed about memory management techniques, segmentation, paging, page faults, virtual memory, and page replacement algorithms. This is more than enough for the exam. And if you have any questions, do get back to me. Thanks, guys. Good luck.